Okay, so now looking at question 6 is the Doppler effect question. Question 6 says a siren of stationary ambulance emits a sound wave of frequency 280 hertz. A car is moving towards the stationary ambulance at a constant speed that is 310 meters per second, lower than the speed of in the air. Okay, and so this is not the speed of the ambulance, that's how much lower it is than the speed in the air. Define Doppler effect. It's the apparent change in the detected frequency as a result of the relative motion between the source and an observer. Okay, so yeah, it's simply the as you said, the apparent change, the observed difference in the frequency heard as the result of relative motion. That means there's relatively a difference between my motion and the motion of the source, or the listener's motion and the motion of the source. Calculate the frequency of sound detected by the driver of the car. Use the speed of air as 340 meters per second. So calculate the frequency of sound detected by the driver of the car. So let's quickly see, what do we have? A stationary ambulance emits a sound wave of 280 hertz. A car is moving towards them. 300. Okay, so just the frequency of the sound detected. Excellent. Okay, and here's his attempt. If I look at his formula, I'm sure his formula is fine. If he's working it out fine. What I prefer to do is I prefer to use a single formula. The frequency observed is equal to the velocity of sound minus the velocity of the, is it the listener? Yeah, the velocity of the observer divided by the velocity of this the medium or the sound wave minus the velocity of the source times the frequency of the source. Now I always use a negative in my formula, and that just helps me. And then depending on their relative motion, are they traveling towards each other or are they traveling away from each other? That will just change this. So whenever they're moving in towards each other, okay, then the resultant velocity, I will choose no, let me not say it like that. So let's look at this top part. We have the velocity of the sound traveling towards the observer, okay, and the velocity of the sound towards the observer. Now the observer is either traveling towards the sound or he's traveling away from the sound. Okay, so this is the sound and that's the observer. So if he is traveling towards the sound, they have opposite directions, and so I'll make the velocity, so I'm taking the velocity of the sound as positive, and so since this one is in the opposite direction, I will make his velocity negative. Okay, so this one, in this case, he is traveling towards the source, and so that one will be positive. Okay, and then in the bottom, the vehicle is stationary, so it doesn't make a difference. But let's say the vehicle was traveling towards the source. So obviously now the sound is in this way. Okay, the observer is hearing it from here. Is this here? Okay, and so let's say the vehicle making the siren is traveling in the same direction as the sound. Then this will remain a negative, okay, because he is still going in the same direction as the sound. But if he was driving in the opposite direction, then this one will become a plus, okay, because now he will also get a negative. Okay, And so in this case, his is correct. So because what will happen to the velocity of the listener? Well, the velocity of the listener is traveling towards the sound. So him and the sound is in the opposite direction, so his negative will make that a positive. The velocity of the source is stationary, so it doesn't matter. It will, that plus or minus, it won't make a difference. Okay, so the 340, so the velocity of sound, or the speed of the sound is 340 plus, and now very clever here of him is he multiplies or he takes the difference between sound and the motion of, because that's what's given here. And so that difference is 30 meters per second. And so that's what we put in here, 30 meters per second, or 340 minus 310. Okay, and then at the bottom we only have the velocity of the medium, which is 340, and then the frequency of the emitted sound is 280. Now I just want to see here that he's calculating it correct, because the 280 should just be on the side. He shouldn't multiply it with a 30, but I'm sure it wouldn't. That's not how he did it. So 340 plus then the 30 meters per second, okay, divided by the 340 is 1.8 times the 1.08 times the 280. 304.71. Perfect. Oh, well done. Okay, that is the frequency observed by the listener. How will your answer in question 6.2 be affected if the car moves away from the ambulance at the same constant speed? So a car is moving towards. Now, what if he was moving away from it? So now you can see he's hearing it at an increased frequency. If he was moving away, this would be a negative. The whole thing would be negative. So he would be moving away from it, and he would hear it at a lower frequency. So explain your answer. And so if the observer was traveling away, so it will be smaller than. If the observer was moving away from the source, he would be traveling in the same direction as the sound waves, and therefore his observation of the waves would be at a lower frequency, because as the wave is going, he's traveling in the same direction, while if he was traveling in the opposite direction, he would be driving into the waves, in a sense. So he will encounter them faster because of his relative motion to the waves. And so that has the same effect here. Explain your answer. I did now. Let's just see, it will get smaller. He didn't explain his answer here. Question 6.3, give one use for a Doppler flow meter. It can determine the rate at which blood flows. Yes. Okay, that's a good example. Question 6.5. When a line in a hydrogen spectrum is measured in a laboratory, it has a wavelength of that. The same line in the light of a distant star has a wavelength of that. Is the light moving towards or away from us? So a wavelength would be the length from, if we have a wave like this, there's our wave, then the wavelength is the distance from here to there. That's the wavelength. Okay, so if something is traveling away from us, then this point and that point will be stretched out, because the moment this point was emitted, okay, if this was stationary, then by the time this point is emitted, that would be the wavelength. But now this thing is moving, so before he can emit that point, he's already moved a certain distance, and so this wave is stretched out. Okay, So that is why if my wavelength is larger, and that's what you can see here, the wavelength is larger, that means it's moving away. And I've just done the explanation again. Don't just answer, but give explanations, especially if they ask it.